Hi everyone, in this video segment we will be covering inductive electron withdrawal and its effect on acidity and basicity. Quick preface here, in the last two segments we talked about electron withdrawal via resonance and electron donation via resonance. Here we are talking about an inductive effect, which is pertaining to sigma electron density, okay? Resonance is all about pi electron density, inductive effects are sigma electron effects. Now, inductive electron withdrawal will result in an increase in acid strength. The effect of the inductive group is kind of twofold, okay? This is important. The inductive withdrawing group will not only destabilize the acid form, but it will stabilize the conjugate base compared to a molecule where there is no inductive withdrawing group, okay? So the acid becomes more acidic. It is destabilized by the withdrawing group, the inductive atom or group. But it is the case that that inductive withdrawing atom or group will stabilize the conjugate base. All right. Now, induction, specifically inductive electron withdrawal, will best distinguish the difference in acidity between acids when the atoms bearing the acidic proton are the same, but there is a difference in terms of the substitution of these inductive atoms or groups. Okay. Let's look at a couple examples here. And before we do that, I want you to keep in mind always with inductive groups as opposed to resonance groups. With inductive groups, there is a strength and a proximity effect. The stronger the inductive atom or group, the more it withdraws, the more it will increase acidity. Okay, the stronger the group withdraws, the more acidic the acid form becomes. When we think about proximity, the closer the inductive atom or group is to the site of the acidic hydrogen, the more it has the capacity to withdraw, okay? So that's important. The closer it is to the acidic hydrogen site, the more it will withdraw. We're going to contrast both of those ideas, strength and proximity, in this example. So we have 4 carboxylic acids. The acidic hydrogen, in each case, is bonded to the same atom, oxygen. They're all the same functional group, but what's now differing is the substitution of the structure with these inductive atoms. Halogens, chlorine, fluorine, bromine, and iodine, can function as electron-withdrawing groups. Note that these atoms, right, these halogens are not bonded to the acidic hydrogen itself. Accordingly, they are functioning as accessory atoms. They are inductive atoms in these structures, okay? And when we think about electronegativity, remember, fluorine is more electronegative than chlorine, which is more electronegative than bromine, which in turn is more electronegative than iodine. The most electronegative halogen is fluorine. The least electronegative halogen is iodine. So what we see in this comparison is there's an increase in acidity going from left to right, because in the first three, we have an increase in the inductive capacity of the inductive atom. Fluorine is more withdrawing than chlorine, and chlorine is more withdrawing than bromine. You can kind of consider that the sigma density is being shifted a little bit towards the inductive atom, that it's pulling it a little bit. Again, this is not a resonance effect. You can think about this inductive atom as just kind of tugging on the electron clouds over the atoms. It's pulling a little bit. And the fluorine has more of a pull in its direction than the chlorine or the bromine. Now, the difference between these two structures is the location of the fluorine atom. Notice how in the right structure, the fluorine atom is actually closer to the site of our acidic hydrogen, and in this structure, it's further away. When the fluorine atom is closer, its inductive capacity is greater, okay? You can kind of think about it in this way. If each atom has electron density around it, okay, in the right example, the fluorine has to pull through a couple atoms, just 2 of those. We've labeled them with our dots there. But this fluorine has to pull through 3 electron clouds. And so the effect felt by the oxygens in each of these cases is different. The fluorine that is closer pulls more strongly, okay? So we have this idea of strength and of proximity as being a factor in the inductive capacity of an atom or group. Let's now look at the conjugate base stabilities. Okay, so we're going to deprotonate all of these carboxylic acids, now looking at the carboxylate ions. Going from left to right, we have increasing conjugate base stability. This is the weakest base. This is the strongest base. The inductive atoms will act to stabilize the negative, okay? This naturally in the carboxylate resonates, the negative charge. And the induction from your halogens is additionally helping to provide some stability. You can think about that inductive withdrawal as being stabilizing, okay? It's stabilizing to the conjugate base, and it helps to deconcentrate the negative charge on the oxygen, okay? It's pulling it a little bit, making it less concentrated. Whereas in the far left example, you've got the bromine, which is less inductive. So it's just not stabilizing that conjugate base to the greatest extent, okay? And of course, chlorine is more inductive than bromine. Therefore, this ends up being a weaker base, a more stable base, because of the chlorine's inductive capacity to pull as opposed to the bromine, all right? So again, strength and proximity are both factors when it comes to looking at inductive atoms. There's a typo by Ryan, inductive atoms, okay? And we think about the strength, the proximity, always when we're looking at inductive groups. I want to give you one other example of an inductive example. Here we have two carboxylic acids, all right? And the one on the bottom here has a nitrogen, which is positive. It's fully protonated, okay? That positively charged nitrogen is actually an electron-withdrawing group via induction. It will very strongly pull electron density this way, which causes this acid to be more acidic than this one. So we're going to say this acid is more acidic. It would have a lower pKa, and this acid is less acidic. The acid above is less acidic because there is no electron withdrawing group. Okay, here we have an inductive electron withdrawing nitrogen. That positive nitrogen is actually very, very strongly withdrawing. Okay, now to even give you a more nuanced comparison, let's say you had two compounds, each with phenolic OH groups. We're going to look at one having a fluorine and one having an NH3 plus group. We think about fluorine being a very electronegative atom, right? However, I want you to understand that in organic, it's even more nuanced than that. We can't just use our rules and our understanding from Gen Chem to get us through. We have to create new schemas, new understandings. And the idea is that this right structure is going to now have the more acidic hydrogen. That hydrogen is more acidic than that one because the NH3 plus group is actually more strongly withdrawing. We're going to say that it's more strongly withdrawing, okay? So we have fluorine being electronegative, yes, but this NH3 plus group is very withdrawing. A positively charged atom has a deficiency around it, right? So what does it do? It yanks on nearby electron clouds, pulling electron density closer to it. Okay, another more nuanced example. You'll also note down here I said that carbonyls are inductive. Let's look at an example of that. We're going to have these two alcohols. This is an alcohol and this is an alcohol. The more acidic species is the one on the top. Neither of them in the conjugate bases, let's draw the conjugate bases real quick. Neither of them can resonate their negative charge in the conjugate base, so they're both isolated. However, it is the case that in the structure, the carbonyl, the C double bond O, possessing this difference in electronegativity between the carbon and oxygen, has an inductive withdrawing effect. There is an inductive withdrawing effect. However, there is not that inductive withdrawing effect. Because of the inductive withdrawing effect, we're going to say that this is then a more stable base. The induction is stabilizing it. Stable equals weak, weaker base, stronger acid. Okay, this is the stronger acid. So I encourage you, again, to think about the difference between induction and resonance and understand that with induction, we have to consider strength and proximity and develop a more nuanced understanding of what we consider to be inductively withdrawing groups.